Ready, let's get started. So we have now finished two modules. We finished state estimation, we finished control. Yeah, the presentations are on Friday, were on Wednesday, were great. And today we're going to start search, and we have three-ish lectures of search, and then we'll do some learning. Okay, some logistics. I know that we've been having some card troubles. So let's just extend the deadline till Sunday for everyone. So whoever's having car troubles, the TAs are fixing all the cars, I think, this afternoon that have had trouble. What happened? Did you guys have trouble? It's still drifting. Which car number is it?
We had 29, but we brought someone else to finish the project.
Okay. Since I'm not in the lab, I don't exactly know what the issues are. So how about you just tell me and I'll make sure they're fixed. Right? Just email me and I'll make sure they're fixed. At least we discussed this morning, there were 3 cars that had some trouble. I'm just, whoever else has trouble, let me know. And yeah, the point is not to, the point is not to like make you guys struggle with hardware, but hardware is hardware and it behaves the way it behaves. And so we tested all the homework on the cars before the class. It's just, it does what it does. So, but yeah, don't worry about the deadlines. Let's just try to like learn how to do this stuff. Okay. So yeah. Tentatively due February 23rd. If you have problems, we can extend it. It's fine. And then we'll release homework for tomorrow. You guys will get 2 weeks to do it till the 6th. And then you'll have 2 weeks for your final project till the 20th. Basically till the end of finals week, you can just get it checked off at any point. Okay. Good. All right, here's a little quiz. Lyapunov functions are always positive, negative, can either be positive or negative. By positive, I mean including C. Seconds. Alrighty. The answer here is positive. Lyapunov functions are positive. Their time derivatives are negative. And so the reason they work is because you sandwich a positive number, which is always reducing. So it has to go to 0. Okay. But today we are not going to talk about Lyapunov functions. We're going to think about planning. And so we've talked about state estimation, control, planning. And so we're going to try and formalize what planning is. We're going to think about why it's hard, try to visualize what makes it hard. And then we're going to think about how we can start approaching this problem. Okay? And next class, we'll try to come up with some practical solutions. And the class after that, we'll try to make the solutions better. Okay, so if you go back to our lecture 2, right? We want a robot that interacts with the environment to go from sensors to actuators. We had this loop where we had a world model. State estimation tells you where you are, so it goes into your world model. And then you have planning, which tells you a good global path. And you have control, which tells you how to follow the path. And so we went kind of topsy-turvy, and then we did state estimation, we did control, but now we're going to do planning. Okay? And so planning, as opposed to control, is really about finding a global path through the space. So if you're a helicopter, it tells you the path you need to follow to get to your target, but it doesn't tell you the lowest level controls. That's what controls do. Right? And so controls assume that you have a path. Planning gives you that path. Okay? And so we're going to focus on planning for the next few lectures. And so planning kind of fits nicely into the sense plan act paradigm. You have sensing, which tells you where you are. You have planning, which tells you how to avoid your obstacles. Often planning is about avoiding obstacles while minimizing costs. And then control kind of keeps you on track. So control is really about stabilization. Planning is really about finding a collision-free path through high-dimensional space. And state estimation is about managing uncertainty. Okay? And so we talked about state estimation, we talked about control, and now we're going to talk about planning. Okay. So let's think about this example of flying from Seattle to LA. And so if I'm going to fly from Seattle to LA, I'm going to start by getting to the terminal, boarding an airplane, getting off the airplane, taking an Uber or whatever, right? But then I'm going to break those down into smaller steps, right? So I'm going to planned getting the terminal as like getting onto the I-5 and then driving down and then getting off on the exit and so on. And similarly, you want to like plan your route in the airport, plan your route once you're off the plane. Right? So there's like different levels of planning that you do. The highest level planning in terms of like task planning. I want to get to the airport. I want to get on my flight, get off the flight. Then within each of those steps, you kind of break it down into smaller parts. And then you kind of like keep breaking those down further and further and further until you finally start asking the question is like, how do I actually take the first step of this, which is getting out of my house, right? And so in terms of in planning terms, right, this is like a hierarchical planning scheme. So you have a highest level plan, and then you break that down into smaller and smaller and smaller steps until you're planning about motion, right? So I'm thinking about like, how do I get out of my house? It's like, how do I move my joints and limbs until my or me as a human is able to get out of my house, right? And so I'd argue that the top few layers are kind of what you call task planning. And the bottom layer is really what you call motion planning. And so it's like, how do you plan your motion to get you and your suitcase out of the house while, avoiding colliding with random stuff, right? And so we're gonna specifically consider the problem of motion planning. The planning is like a really old field. So none of you are old enough, but neither am I. But in the 90s, there was this like big focus on planning, and there was this thing called expert systems that people used to use. It is like the deep learning of the 90s. And so it is basically about like when you have a set of logical predicates that an expert specifies to you, how do you draw inferences from those predicates to make decisions, right? So a lot of that is like basically about how do you chain together logical predicates to make decisions. So you do that kind of thing for solving Rubik's cubes or playing chess or I forgot what this thing is called. Whatever, this 8 puzzle or 16 puzzle. But these are all like what you'd call typical planning problems. And these planning problems are discrete state spaces, well-defined transitions between those predicates, right? Lots of domain knowledge. And it's led to a lot of interesting algorithms, right? A lot of these like graph search algorithms, you've heard of A-star, Dijkstra's, like all of them, a lot of them came from some version of planning. But what we're gonna think about is a different problem, which is the problem of motion planning, right? And so the problem of motion planning is not like, do I go, to the airport or do I go to the car? It's like, how do I move my joints through space and time while avoiding a bunch of obstacles, especially when I'm controlling like 50 joints at once. Right? And so what makes motion planning hard is that the state space is continuous. Your action, you have to consider dynamics. You can't just teleport through space, like your joints move in a certain way. You often have uncertainty. You have these non-holonomic constraints. So for instance, you've seen your musher cars, you can't just like go sideways, right? You have to like follow the tracks of the car. And so if you're planning, you have to like account for the dynamics of your system. And that becomes really hard in high dimensional continuous space. That's what's going to make motion planning. So this motion planning is often called the piano movers problem. And here's an example from the 80s. But it's basically, you can see that they're trying to move like, this is like a maze kind of thing where you're trying to extract an object from somewhere. But what they're trying to do is like place furniture inside a room, but you can only translate and rotate the furniture, right? But you cannot collide with anything else. And so the problem is hard because you can't like teleport, you can't fly over the objects. You have to like consider their collisions with things, and you have to like account for that while planning, right? And so for instance, some things might be too tight to get through, so you have to like plan for how they collide with other objects. As the number of objects and number of degrees of freedom goes up, that gets harder and harder. And so this is the simplest motion planning example. And then it goes harder and harder and harder. You can show that it's like harder than it's what you call p-space hard, which is harder than NP, extremely hard. Also shown in Friends. I don't know if any of you watch Friends, but there's this scene where Ross is pivoting his sofa up the stairs, and that's essentially the piano movers problem in action. And I thought that was cool. But basically, most motion planning problems are like generalizations of this piano moving problem, where you're trying to like navigate through free space with a constrained system while not colliding with anything, right? So you have to account for the constraints of your system. You can't teleport, you can't fly, but you have to avoid collisions with things in a really tight constrained space. Okay. And this is, the piano mover problem seems easy, right? But when you like go to problems that you actually care about, like this is a Honda humanoid, this is one on the International Space Station, right? You're trying to plan motion to, for instance, pick up a table or plan motion to like get through space while holding onto a guardrail with a really high degree of freedom system. You have to do it fast enough and on low compute systems, that becomes really hard, right? And so, I think like if you look at any of these like systems in space, etc., they're not running NVIDIA GPUs, right? They're running Pentium 3s or 4s or whatever. And so it's like you have to be compute efficient while dealing with really, really high dimensional systems and dealing with lots of constraints, right? So if you didn't deal with the constraints, this robot would just fly off or it breaks up. Okay? And so you have to be highly reliable, pretty quick, and deal with high dimensional systems. And so this is kind of like the general problem motion planning. If you ever see problems like this, like with a bimanual arm, you'll see that the arms have to avoid each other. Right, so you're in a tight space, you have to avoid each other while like moving fast and doing motion. So that's up on the right. We have whole body planning, which is up on the left, which is like you're trying to move the whole humanoid at once. And this is more conventional, like most factories will deploy motion planning systems to get quickly from one point to another when there's obstacles in your system. Right? And so most motion planning problems that you consider are about getting from point A to point B while avoiding obstacles and obeying the constraints of your system. Right? Okay. What makes this even harder is when you go from these kinds of like problems that you can compute offline. So a lot of these problems you can compute offline. Right? You compute a path to go from here to here. You execute the path with a controller. But what makes this harder is when you have to do real-time planning. Right? So it's like you're planning and then a human comes in your way. You're like a robot arm, which is planning to move from point A to point B. Suddenly a human comes in your way. Your plan has to be different. You have to do that on the fly and you have to be safe, right? So any safe system needs you to be able to do real-time replanning. And that's kind of what makes this problem really hard. And so this is an example from Willow Garage, makes the PR1 and PR2 robot, but you can see that like people will stick their hand in the middle and the robot has to kind of get around. Another example is from like autonomous driving systems where the map is not fully known. As your map is not fully known, you're building the map on the fly. As you're building the map on your fly, your plan changes. You realize that I can't go that way. I have to change my plan. And so you have to be able to really quickly incorporate new information into most planning methods. And so as opposed to like things like reinforcement learning, which you could take 50 hours to train offline, like planning really has to be fast and really has to be real time, right? And so if you're driving a car around, you need to be able to make new decisions in real time or close to real time. Okay. The other nice thing about motion planning methods is that they're often very universal. In the sense that there's like a single algorithm that works across many systems. So if you look at the state-of-the-art motion planning algorithms, some of them from SID are very old. A lot of them are like the same algorithm, just applied to different systems. You just change the model, but it's the same algorithm. Whereas if you look at other fields, often you have per problem solutions, and motion planning algorithms are beautiful because they're like really, they're basically search methods that are scaled up to continuous spaces, but the same method works across lots and lots of different forms. Another nice thing is you can prove things about them. You can say that it's going to converge, or you can say that it's going to be this suboptimal, or you can say things that there's these algorithms called anytime algorithms where you can show that they'll continue to get better over time, right? And so it's like a really beautiful field of work. Right? But we have to solve it, right? So we have to figure out how to motion plan. And so we're going to try to take this step by step. We'll start by specifying and formalizing the problem. We'll then think about what makes this problem actually hard. Let's try to like visualize the problem difficulty a bit more. And then let's try to think about solutions, right? So I like, whenever I think of a research problem, I want to start by understanding what the problem is, understanding which cases make it hard, and then we can think about approximations that are tractable. Okay? And so that's going to be the structure of our lecture today. We'll start by formalizing what the problem is. We'll talk about what makes it hard, mostly through some visualizations and examples. And then we'll take a start at solving it. Okay, so let's start by specifying the problem. Now, when we're specifying the problem, we need to specify a representation of our problem that can work across many different cases. So we said we wanted to work for a humanoid, for an arm, for a snake robot, for a piano moving in space. You kind of want a generalizable representation that we can use across lots of problems. So for instance, you have a problem of a translating triangle, kind of like your piano. You have a problem with a 2D planar arm moving through space while avoiding obstacles. You have a problem like a race car, like you guys are doing, or a thing like a robot arm, like we have in the lab. And all of them have to have like some shared formalism that we can use across them, right? They seem like super different systems. And so what we're going to try and do is define a formalism that we can use across all of these platforms. And so the key idea we're going to talk about is something called the configuration space, often known as C, right? So the configuration space, or the C space, is a manifold that contains the set of different transformations that are achievable by a robot, right? And so essentially what that means is like, if you have a robot arm, the configuration space for that robot arm is the set of all joint positions that that robot arm can take, right? Or if it's like a race car, it's going to be your X and Y and theta, right? And so the reason you have configuration, so note that configuration space is not world space. So when I think about a world space, I think about 3D space, right? 3D space, like this is where my hand is, and this is like Euclidean space. Configuration space is not that. So we'll go through a bunch of examples, but configuration space is basically a vector space or manifold of the different settings that the robot can be in, right? So for instance, for a 2D planar arm, the configuration space would be theta 1, comma theta 2, right? Which is not world space. Like the robot exists in world space, but the configuration space is like, what are the configurations of your system, right? And what makes it tricky is that your robot is often operating in configuration space. That's how it's moving around. But the obstacles in the world are in world space, right? Like there's 3D obstacles in the world. And you have to deal with these obstacles in world space while dealing with configuration space. It's pretty abstract right now. Let's make it a little more concrete, right? But the key thing to remember is configuration space is a manifold of the transformations that the robot can achieve. Okay, so you can kind of think of it as like configuration space is like a high dimensional vector space. And like every possible state that the robot can be in will be a point in configuration space. And what you're really trying to do is figure out a path through configuration space that avoids obstacles while getting from point A to point B. Right? So robot arm starts here. You want to have it go here, avoiding an obstacle in the middle. Your initial is some configuration space point, your final is some configuration space point, and you're trying to figure out a collision-free path between them. Okay, so let's look at some examples. So you can start by looking at this triangle example. So you have a translating triangle. The triangle is moving in the plane. And so you have this Cartesian product. You have the configuration space is X position and Y position, right? And so you have a R2 configuration space, as in every position that the triangle can be in is an X comma Y position. And so it's in R2, right? If you have a two joint planar arm, the configuration space is equal S1 by S1. And so S1 is basically a circular space because like you can think of every joint as being a circle, right? Like it's an angle. It's an angle that wraps around, right? And so you have the circular group S1, you do a Cartesian product for the first joint with the second joint, right? So all the configurations that your two joint arm can be in are S1 cross S1. Yeah. Yeah, so there's a choice you can make on whether you choose to do a unrestricted cross product and then like say which parts of your configuration space are infeasible after. Or you can choose to like restrict your configuration space. They're kind of the same. So often what you do is you do an unrestricted cross product and then you like say that like these are infeasible parts of your configuration. Good question. But viewed graphically, you can kind of think of it as like it's a theta 1, theta 2 space, but it has wraparound. Right, because it's angles, it wraps around. And so it kind of looks more like a torus. Right, so you have like theta 1 goes this way, and theta 2, for each theta 1, you can have a theta 2, which goes this way. Right? If you want to visualize the configuration space here, it looks something like that. And so what's going to make this tricky is when you have like when you have an obstacle sitting right there. Right. So you can't like, if I want to get to, for instance, this angle, I like cannot just like, I cannot just send my robot this way. It's going to hit the obstacle, right? And so what I have to do is like move this thing over like this or something like that, and then like get through and then flatten out. Yeah.
So in order to do that, you would model what parts of the state would have the arm colliding with.
Exactly. And that's going to be tricky, right? So we'll talk about that. The example that you guys care about is the race car, right? So in the race car, you have X, Y, theta. So you have X and Y, which is in R space, and S1, which is in your angle space. And so this is a group that you often call the special Euclidean group, or SE2, right? And so SE2 is going to be X, Y, theta in the plane. The car's not going to be flat, and so it'll stay in the plane. And so you can have like a bunch of different robots. Each of them will have their own configuration space. But when we think of these planning algorithms, we're just gonna generically operate on the configuration space under generic assumptions. And then you can instantiate them with each of these specific robots. So for instance, you might have like mobile robot translating R2. We'll have mobile robot translating and rotating like your race car, that's SE2. You can have a spacecraft which can move in 3D and have all sorts of rotations. That's SE3. And so you can have a bunch of these, right? So we don't have to go through these examples, but they're all just like different instances of a configuration. Yeah. Okay. Now, as Ruin was alluding to, right? The tricky part is when you have obstacles. And we're trying to find collision-free paths through space. And so the way that obstacles are specified, yes. So I guess the way you're going to model, this, you're saying for the race car. So like for the race car, like basically different configurations of different transformations that the robot can take are like where it is in X, where it is in Y, and then like where it is in theta, right? And so like you can't transition from every configuration to every other configuration, but the space of configurations it could take are X, Y, and theta. Right. So the way that this often will work is you'll define a space, and then you'll often have like which transitions are possible in your space. Right. So the space of possible transformations your car can take are X, Y, and theta. And then you can't transition from, for instance, car here to car here. So like when you're planning, you can't like teleport. And so what you'll do is you'll try to solve constraints to see like which configurations can get to which other configuration.
Not necessarily like what this necessarily what action
No,
you can take.
no.
Right.
Like the state of the system more so. Yeah. The actions are more like edges. So you can kind of think of the C space as defining the nodes for a graph, and the actions are like the edges which tell you which nodes are connected to each other. Good question. Okay. So we're thinking about obstacles, right? And so obstacles are typically specified in world space. Right? So we've been talking about configuration space. Like let's say for a robot arm, configuration space is like theta 1, theta 2. Right? So it's like theta 1, theta 2. But obstacles are in world space. Obstacles are not in the like joint angles of the robot. The obstacles are like sitting at like this coordinate and this coordinate. Right? And so typically you're going to like specify something called workspace or workspace, W, which is typically in R2 or R3. And you're going to have obstacles being sets inside the space. Okay? You're going to say like an obstacle is like a subspace, right? It's going to be like a subset of this space, which could be like a polygon or a circle or a cube, like, or a table could be an obstacle, like any like subspace, but it's going to be in world space, right? So the important thing about obstacles is that they're not in configuration space, they're in world space. But your robot is planning in configuration.
few errors made by the robot that can actually remove errors. Like, do those locations also in the configuration space?
Do errors? Yeah, so it would be like the way you'd move your robot would be in like joint angles, and that would be it. Like if you made an error there, your error would be in your configuration. But your obstacles are specified in space, and so one thing that would be interesting is if you're estimating where your obstacles are, that is in world space, and then you have to project it into the figure. You have to also project it. Okay, so obstacles are in world space. And we're gonna call like the shape of our robot A. And so our robot is not a point. Our robot is like a physical body that has like area, right? And so like for any configuration Q, you're gonna say that AQ is like the physical space occupied by the robot, right? So for instance, if you have a robot arm like we've been drawing, and let's say this was theta 1, let's say this was theta 2, right? Like this whole area is going to be your AQ, right? And this is going to be your obstacle. Right? So for every Q, you're going to have an AQ, which is like a map that tells you what is the area that your current robot is occupying in your world space. And your obstacle is also sitting in world space, right? And so the tricky part about motion planning is that your obstacles are nice and often like polyhedral or something in world space, but they're nasty in configuration space, right? And so what you need to do is you need to map your obstacle from world space into configuration space, because that's the place you're going to plan, that's the place you're going to. And so often when you write COBS, it is the region of configuration space where your robot, your obstacle are colliding, right? So you can think of this as a set of configurations in configuration space where the robot body is colliding with the obstacle, right? Where the intersection is non-zero. And so it's like not a trivially specifiable space, in that it's like you're trying to pull an object from world space into configuration space, right?
It's like really hard, especially.
Yeah.
if they're-
Yeah. It is. And we'll talk about that.
The area of
Yeah.
like one area and one measure.
I'm just talking about the body of the robot. So it's like, imagine that it's like a volume in world space. Like for instance, it's like a spacecraft, right? It's like for this X, Y, Z roll pitch yaw, like what is the volume of 3D space that is occupied by your robot? Right? Or if it's like an arm, it's like what, like let's say the arm was at theta 1, theta 2, right? You're like given your geometry of your arm that you know, it's going to be like this area is occupied by R. Right? And so like this subset of points is going to be your AQ.
Area function.
You have to know the model. Yeah, exactly. So in most cases, you'll know the model of your robot at least, right? And so you kind of know this map. It's just like not trivial to compute this space, like Zoe was getting at. Your question? No. Okay, so what's going to make this tricky is that you have to pull your obstacles from the workspace into configuration space. And then you have to plan a collision-free path in configuration space with these nasty looking obstacles. So we'll see how the obstacles project. But you often call C-free as the like collision-free part of your configuration space. And you're trying to find a path through the collision-free part of your space when you have these nasty non-convex obstacles. Okay, so let's look at a few examples, right? So here's the simplest one. You have a triangle that's translating, right? Your triangle is translating, your obstacle is a rectangle. And your configuration space is X, Y. Your area is this like triangle, right? Now, like what does the obstacle look like in configuration space? So our configuration space, remember, is going to be an X, Y, right? Now, if I had to like pull this obstacle into configuration space, what would the obstacle look like? So we're trying to say like, what are the configurations where the obstacle and the robot are in collision? So, yeah. Right. Yeah, almost, but it's basically, you can kind of think of it as like, you can have your triangle intersect here. You can have your triangle intersect here, right? You can have your triangle intersect here, right? And so like all of these points will have some intersection. And so when you pull it into configuration space, it looks something like that, right? So it's like, you can think of it as like translating this thing this way, translating this thing this way. At least one point is going to be an intersection. And if you like move it over here, it's obviously an intersection, right? And so if you had to like pull this obstacle into configuration space, it looks like that, which is not so bad, right? For a 2D thing, but it's going to get worse. Does that make sense? Right, so this is something you can compute using something called a Minkowski sum. If you have two sets, you can take the sum of every element pairwise. That's what you call a Minkowski sum. But in this case, you can compute it that way. You can't do that in all cases. But like, if you want to ever compute a configure of an obstacle in configuration space, go through configuration space and see which of those points the obstacle collides with the robot in the workspace, right? So you can kind of think of it as like, sorry. So you can kind of think of it as like there's a Q space. Q space is your configuration space. Q maps into AQ in the workspace. There's an obstacle in the workspace. You see when these two are intersecting, and that gives you an obstacle in configuration space, right? And that's where you're going to do all your planning in. So natural question to ask is, why can't we just do we have all this nasty pulling from one space to another. Why can't we just do all our planning in the workspace? Like, man, in the workspace, it looks nice and simple, right? Like why can't we do planning in the workspace? Yeah. So you can't just like if you can do it for this problem, right? But you can't do it for a general problem with like a 30-degree of freedom manipulator. You can't just like teleport to whatever space you want in the workspace. You have to obey the constraints of your system by taking action. That's what makes it hard. So let's, this is basically what I drew out. Now, if you allow the system to rotate, right? So you let it translate and rotate. Now the configuration space is going to be X, Y, theta, and your obstacle is going to look like that. So the way you can think about it is that you have like many slices. Each slice is like basically that thing, but it's just like a rotated slice, right? And so you can kind of compute it by like freezing the robot at every different rotation, moving it around, computing the obstacle space, and then changing the rotation, recomputing it. That's why it looks like, you can see each of these slices is basically the same thing as this. And so if you go from just 2D space to allowing it to have rotation, now my like obstacle looks a lot more nasty, right? And so if I have to like plan to get around the space, I can't just like fly through the space. I have to like navigate around. Right? So, but this is like a dead simple system. It's just like translation and rotation, like a silly system, right? Questions? Does it make sense? Think of this as like a series of slices at different angles. Now, if we had a system like this, right, which is a robot that can like translate and rotate, like your car, right? If you want to compute the the configuration space obstacle, you would again like translate the car all over, right? If you notice the like obstacle is no longer like a rectangle, and so you'll see that like you can translate it all over. You'll start seeing again like slices of different shapes. And when you add it up, it looks like some like nasty looking non-convex thing. Right? It's a little hard to visualize. I'll show you some better ones. But it's like, this is kind of your 3D visualization where it looks like this nasty looking 3D thing, and you have to like navigate from here to here while avoiding gaps. Now, where it starts to get really hairy is when you have like a robot arm, right? So if you have like a robot arm, you have to like consider different joints, and let's say those are the different obstacles, right? If you project each of those obstacles into configuration space, it starts to look something like that. Right, so the different colors are projecting onto their corresponding configuration space obstacle, and that looks really nasty, and you're trying to get through that space. And similarly for here, for instance, you're trying to go from some QA to some QB. There actually doesn't exist any path that gets you there. But when you just look at that thing, you'd expect there to be a path. But when you pull the obstacle from world space into configuration space, you'll see that there exists no real path to get from there to there. Right? No collision-free path exists. And so problems that seem simple in workspace might be quite complicated in configuration space. Can I buy that with me? Okay. So the general problem we're going to try and solve is kind of define something like this. We're going to say that we have a workspace, which is either R2 or R3, radial space. We have an obstacle region. It doesn't have to be a single region. It can be a collection of regions. Okay? We're going to have a robot, which is defined by some A function, which maps the configuration into an area. You're going to have the configuration space. You're going to have an initial configuration. Let's call it QI. You're going to have a goal configuration. Let's call it QG. And your goal in motion planning is to compute a continuous path through the free part of collision space, where it starts at QI and gets to QG. Right? And so you have to basically solve this search problem where you're trying to get from, like, you're trying to find a path that gets you from QI to QG while staying in the collision-free part of configuration space. Yeah, that's the problem. And sometimes you'll have a cost, like you want to like get there while saving fuel, or you want to get there while obeying other constraints, but not always. Often you just try to find the shortest path. Okay, so here's a visualization I find kind of helpful. It's like this is again a 2D triangle thing moving through space. And if you look at the like planning problem in this case with these obstacles, it looks something like this. You have to like navigate through this like nasty space in order to get anywhere. And so you can see that robot will start moving in a second. But this pink line is showing its planned path. So you can see that it's like getting through space, but it's like, you can see that it's like navigating through this like nasty non-convex space. Right, so it's like, seems like it's pretty simple, but when you like start mapping these obstacles into the space, it becomes really, really nasty, even for a simple robot. And so if you look at the motion that has to plan, it can't like magically go through things. It has to like move and adjust and move and adjust and move and adjust. Right? Similarly, if you're trying to get this robot to over here, you have to do like strange things like that to get there, right? So this is the result of a motion planning algorithm. Okay, so does everyone buy that the problem is hard? Yes? Good.
Hey, just kind of curious, if we have like a software lot that's something that has like a ton of degrees of freedom.
Yeah. Stuff. So often in those cases, you'll use often in those cases, building a model is even hard. And so the number of degrees of freedom is really high. You'll try to use approximations of like, it moves like a lower order rigid body system, or you'll try to do some like model-free algorithm like reinforcement learning. That is a tough problem. Okay, so in certain cases, you can solve the problem using this technique called visibility graphs. And visibility graphs are basically saying when you have polyhedral obstacles, right, and polygon robots, you can like basically construct a visibility graph, which is like which edges, which corners are visible from which other corners. You can plan a path through those corners, and you can prove that it's like going to be close to optimal in many cases. But in general, the piano movers problem or the motion planning problem is what's called P-space hard. That's your P, you have NP, and then you have P-space, and you have exponential, right? And so it's like you can say that you can show that even for translating rectangles, It's a piece space hard problem. And if you consider things with uncertainty, etc., it's like a what do you call it? Next time hard problem. So you can prove that it's hard, but it doesn't mean it's like hopeless. We're going to find like good approximations to make this happen. But what makes it kind of hard is that you're dealing with this like complex non-convex space because your obstacles have gone into configuration space, and you're dealing with this continuous high dimensional space. So like Jordan was saying, you have like a soft robot or something with a ton of degrees of freedom. How do you deal with that high dimensional continuous space? Right? So it scales poorly with the dimensionality of the obstacles and the space, but we're going to find some good approximations. But a planning problem basically takes in your workspace obstacle regions, your configuration space, your start and goal configurations, and gives you a collision-free path, which might also optimize costs. Right? That's going to be our problem. What makes this problem hard for things like the car that we're doing is that it's also not like in some cases, like a robot arm, you can kind of like teleport through space in a certain way. But when you have a robot car, for instance, it's very like the set of next configurations you can move to are quite constrained. Right? So like Marco was saying, you can't like, you can go from this car position to like this and this and this car position, but you can't like magically teleport to this car position, right? And so these are often what you'll call differential constraints, right? So differential constraints would say that like they're constraints on the velocity of your system, or they're like where you're putting constraints in the dynamics of which things you can go through. It's not every configuration can go to every other configuration. And so often you'll put these kind of differential constraints on your system. And another example is like you're trying to park a semi-truck in a parking spot. It kind of has those constraints too, right? It's like you can't just like let the trailer go wherever it wants. It obeys certain constraints. Or another example is like imagine you're flying a plane and one of the wings is on fire and you can only go left, right? So you like really restricted the set of configurations you can go to. And so you're restricting yourself to some manifold of the configuration space, and so your paths become much harder. That's going to happen in your car too. You can't like teleport from here to here. This is why like planning with an omnidirectional base is often easier than it is with like a non-holonomic base. And so that's what's going to make motion planning hard. But motion planning with differential constraints is going to be the same problem setup, but you're also going to take in these state transition equations. You have to find a path where every consecutive thing satisfies the state transitions. Right? You can't say that you can't like jump from somewhere to somewhere if it's not feasible. Right? And so, so the problem with differential constraints is you're trying to go through the collision-free space, but you're trying to obey the dynamics constraints of your system. Okay. So the challenges we've talked about is that computing configuration space obstacles is hard, right? They're nasty, non-convex. We've talked about this being a high dimensional space for a soft robot, for a humanoid, for a snake, whatever, right? And it's like often underactuated or non-holonomic, so it puts additional constraints, right? So these are three hard things. So how are we going to solve this hard problem? We're not going to get something that's perfectly optimal, right? Because you can't. But we're going to find a reasonable approximation, which has some guarantees on like how suboptimal it's going to be. And so the art to planning is figuring out how do you construct the right approximations that are good enough while being real time and operating under the constraints of your system. Okay, does that make sense for why the problem is hard? Okay, and the last bit we're going to try and think about is how do we approach this problem, right? And so what we're going to do in this section, like, in state estimation, our main tool was Bayesian filtering. In control, our main tool was optimal control. In planning, our main tool is going to be search. So how many of you know how graph search works? DFS, BFS, Dijkstra's, yeah? Yes. So we're going to use a variant of these kinds of algorithms, right? But we're going to make it work for this much harder problem. And so we're going to primarily try and convert this motion planning problem, which is really in continuous space with all of these nasty obstacles which are hard to compute and so on, into a search problem. And then we're going to try and solve it tractably. And so it's hard to convert it naively into a search problem because your space is continuous. Search is typically done on a discrete graph. And your obstacles are really hard to characterize, right? I had to like sit and sample every point in configuration space and see which things intersect, kind of a nasty problem. And so it's hard to even characterize the graph that you want, and it's in continuous space. And so we have to figure out an approximation that works well enough. And so the key idea we're going to leverage is something called sampling-based motion planning. And the sampling-based motion planning problem is saying that you're not going to like have a perfect solution. You're really going to rely on sampling. And there's two key tricks in sampling-based motion planning. The first is that you're going to use a collision checker. Right, so rather than constructing an explicit graph, you're going to construct an implicit graph, and you're going to use a collision checker to say, if I was going to go from here to here, will I have a collision or not? So, right, so you're not going to do it explicitly, you're going to do it implicitly. And the second is that you're going to construct a discrete graph approximation for a high dimensional continuous space by like sampling. Right, so you're going to say, I'm not going to necessarily cover the whole continuous space. I'm just going to sample a bunch of points, and that's going to be good enough. Right? And so the approximations we'll make in sampling-based motion planning are just these two. Right? The first is that you may have an implicit graph, and the second is that you construct your graph with sampling. Okay, we'll go into the details of this next time, but essentially you're going to like try and convert the key insight in this whole section is going to be how do we convert planning to a search? Okay. So how do we take going from the red point to the blue point? How do we make it into a search problem? So we can use different techniques for graph search. We can either try to construct an explicit graph, right? So you could say like, I'm going to like try and construct an explicit graph, and I'm going to see which things connect to which other things and try to search through it. But that becomes harder and harder and harder, especially when you can't compute the obstacles beforehand. You don't know which things are. Or what we're actually going to resort to is something we'll call implicit sampling-based search. Right? And so that's going to construct your graph on the fly, and that's going to make it a lot more tractable. Okay, so that's the key insight for next time, but I'll see you guys on Monday. And whoever had problem with the cars, maybe just come talk to me after and we'll sort that out. Awesome, thanks.
So just the estimating on the free space and just do.
We had 29.
Yeah.
12.
Yeah, exactly. And the more sampling you do, the better your solution is. So it's like, it's nice because you can control your approximation. So like you do more and more and more and more sampling, the more compute you put in, the better your solution is. Just kind of.
Is it similar to FPC that you project out from a particular point and then treat?
Kind of. Let's go over the details next time. What's up, guys?
Robot just like, I mean, there's the.
Which number?
29.
Oh, yeah, 30 was.